Good afternoon, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow, from NPTEL. And we are into the 8th live tutorial session of this course for this academic session. And the reflection and interaction. Uh, we all know the instructor of this course is Professor Niranjan Sahu, affiliated to Department of Mechanical Engineering, IIT Guwahati, and I am the teaching assistant for this course. And we shall start our session. Okay, so we should, I believe, start this today's session, right? So as it's expansion and oblique shocks. So we already have discussed quite a bit about expansion waves and oblique shocks. So which basically are, if we move a supersonic flow away from itself, we get an expansion wave, right? And if we move the flow prediction, right? So in this session, what we will be doing is we will be studying, or we will be looking into the questions based on the interaction of expansion waves and oblique shocks, right? So there can be interaction between one oblique shock and another oblique shock, and there can be interactions between. So we shall proceed in this manner. So as we have been doing in these sessions, I said in the lectures of this week, right, week 8, and after discussing the lectures, we shall see some questions. Firstly, we'll see some conceptual questions, right, concept-based questions, and then after that we shall see few numerical the numericals, right? So let's move forward then, right? And after that, in this session, there is I have included one more slide on the doubts from the previous session, right? We had one doubt from one doubt in a question from the previous session. So at the end of this session, we shall also look into it. We shall try to look into it. Right? So moving forward. So there were two lectures in this week's content, right? Week 8. So first lecture was lecture 18, right? So in this topic, first heading is theta beta m curve. So we have discussed this theta beta m curve, right? So I'll just revise this again. It's something like this, right? This is our beta and this is our theta. See, right? And below this line we have this weak oblique shock solution, strong oblique shock solution. So, right. After that, the next heading is shock polar. So this is the main focus, I believe, of this particular lecture, right? So what is a shock polar, right? So a new term has been introduced, right, which has been called a hodograph, uh, which is nothing but we are trying to divide the velocity of this flow into components, x and y components, right? So this is it. It looks something like this, right? Dividing velocity is into early classes, right? I believe there is no issue with it, right? If let's say this is V2, then this is right. So this is our holograph plane, right? Because there are two axes involved in it, so we call it a plane, right? Uh, this is, if you see now, shock polar. You see shock polar, right? Shock polar also, what we do is shock polar is one of the things, right, for different theta values, deflection values. So in that case, we get different scenarios, right? So what we are doing is we are keeping the Mac same, and we are keeping the Mac same, but we are changing the deflection values, right? So in the like this, I'll just put it right. So it is because included locus terminology. So we shall see how it looks, right? So it is something like this, right? So how do we, like, what we can deduce from this particular graph, right? So if you see, this is our graph, right? So if we draw some line from this origin onto this curve, right? For example, let's say this is our sum point. Let's call it capital A, right? So if we join this, right? So the angle this line subtends with our x-axis, right? So this is our deflection. Right? I hope this is clear, right? Now, if you curve more, so if you see, there is some maximum theta value, because earlier we have this has come across to us that the theta has some maximum value for some Mach number. So we have some Mach number. For that, there is some linked theta max, right? Linked theta max. So from the graph also we can see that, right? How we can see that? So if you see, draw this tangent to this curve, right? If we draw tangent to this curve, in that case, this is clearly the maximum theta value, right? Beyond that, beyond this in this curve, right? If we have to draw some line from the origin and it has to touch your curve, so we cannot go further beyond this point in terms of the deflection angle. So this defines our theta max, right? And because it's a hodograph plane, so if you let's say if you again come to this point A, right? So for this point A, the x and y axis are its velocities, right? The x and y components of its velocities can be if drawn on this graph, right? So this is the x component, right? And this is the y component for some deflection angle theta. So this is about the deflection angle, right? From this particular graph, only you want to draw maximum this beta value, right? Please note that this is here. This is not beta, but just b, right? Alphabetic b, right? And English alphabet, right? Not a Greek one, right? So I'll again draw this shock polar, one shock polar, right? Y by a star and x by a star, right? So let's say again we have this point A, right? So this is our origin, right? So if I join these lines, right, so I get theta, right? But how do I get the beta value? Or is it possible to get the beta value, which is the shock wave angle? So we have discussed this in previous sessions, right? And this has also been discussed in the sessions also, right? So what you have to do is, so let's say C and C. So what you have to do is, first of all, draw a line from C towards A, right? You drew this line, right? Now what you have to do is, from this origin O, you have to draw a perpendicular. So if you draw a perpendicular to that, right? So the angle this perpendicular, right? So angle this perpendicular makes with the x-axis, that is our beta value, right? So this is our perpendicular. Right? So this is how, right? Okay. So moving on to next topics, right? So then there are inferences based on this particular topic, right? Shock polar. So basically, these what I have discussed, these are the main points, and based on that, one can infer a lot of things, and one can understand various inferences if there are. Right? So yes, so let's move on to this next topic, which is the reflection diagram is nothing but we have this type of diagram. It's a static pressure, right? And then on this x-axis we have theta deflection angle, right? So we have negative theta and it is positive theta. Okay, right. So it's kind of a lobe, right? So the graph we get lobe, right? So this is for a specific MAC number. We are keeping a MAC value constant, and the static pressure differences for an oblique shock, and the graph we get is something like this, right? So this is not just for uh, one case is left running, right? Right running. So what is left and right is, so if you are standing on facing the this in left direction, in that case we have this case, right? And if the flow moves in right direction, so if the deflection is in right direction, in that case we have this type of as a nomenclature. Left running, where we take it as theta values as positive. So this is the initial static pressure value, right? Upstream static pressure value. This point from where this this is ahead of the oblique shock wave, right? Upstream static pressure value. So this is our pressure deflection diagram, right? Static pressure and theta. Then there are regular reflection of oblique shocks. So which is nothing but, so if there are two walls, right, and there is flow in one direction, right, and there is some this deflection we give to the flow. In that case, we get this uh, oblique shock, right? We get this oblique shock, and this what this oblique shock will do, this will obviously reflect, right? But this flow, what will happen to this flow? It will deflect once here, and then it will again straighten, right? Because it has this wall which is, so this is the this uh, topic, right? The regular reflections of oblique shocks. So basically, what is happening is there is a reflection of this oblique shock, right? This is an oblique shock which is being reflected by this secondary wall, right? So if this is primary wall, right? This is secondary wall. So there is this reflection of this shock. Right? So let's this again there is this intersection of oblique shocks only. This is lecture 19, right? So in this case, families have been discussed, right? So two types of families are there. So one is this opposite family, and then there is same family. So what they mean is if the deflections are in opposite directions. Right? So when we were discussing in this pressure deflection diagram, we saw that the theta value, the deflection value can be as per the nomenclature, positive or negative, right? So the this nomenclature also this plus negative and positive values of theta has to do with the families of oblique shocks, right? So if the deflections are in opposite directions, in that case we call it a this opposite family, right? But if this deflection is in same direction, in that case we call this as same family, right? So I'll just draw so that it becomes more clear, right? Same family of oblique shocks. So if you see, right, and this what we do is from here we again give it some deflection, right? So it was like this, we again gave this deflection to it, right? And in that case we'll again some this shock, right? And these oblique shocks will intersect, and this will get one shock, right? One single shock. So this is about the uh, same family, right? Oblique shocks of same family. Okay, all right. So just I'll like discuss more on this diagram later, right? But then for now we are like good with this information, this much information only. Then there is this opposite family of oblique shocks, right? So so what is happening here? We have this wall, right? And we deflected our flow to this direction, right? We are deflecting our flow to this direction, right? So here was our flow, right? Here was our flow, and we get this shock, right? Oblique shock. And for the this uppercase, we get this shock, and these two shocks interact, right, at this point, right? And then there is related to it also, right? There is so this is essentially our this opposite family of oblique shocks, right? So where these two oblique shocks interact with each other, right? So we saw the same. Then, but then there are this there's more discussion into it, but we'll just restrict ourselves to this much only for this session, right? Because it has been discussed fully in the lectures, right? So intersection of oblique shock. Then there is this same way we have this oblique shocks and Mach wave, this Mach wave, and how these interactions take place has been discussed in this topic, right? And then there is this Mach reflection. So what happens is that when this flow is deflected towards itself, so let's see, we have these two flow is moving into between two walls, right? So we give a deflection at one wall. So what we get is a oblique shock, right? So this oblique shock should this will what happen is that this oblique shock will hit at the upper this wall, and then it should reflect, right? But then what happens is that if this for this across this oblique shock, if the Mach is such that the theta serves as a value more than the time of this shock and oblique shock, and M2 is downstream of shock. So if this M2 serves this theta serves for this M2 as greater than theta max, right? Deflection angle. In that case, oblique shock is not possible, right? So what happens in that case is that theta max, what we get is a normal shock, right? So the shock with the oblique shock, right? And what we get there is uh, this Mach line, right? For this type of these type of interactions, right? Yes. The type of curve, the from the interaction, what we get is a curved type of shock, right? Okay. So then the last topic was wave reflection from a free body, right? So one example of this free body interaction of either a shock wave or expansion wave is this nozzles, right? Right? Nozzle in over expanded case, where the exit pressure is less than the ambient pressure, right? So in that case, what happens is that if there is oblique shock, so the reflection of this we have initially if we have oblique shock, so reflection of these oblique shocks gives expansion waves for this free boundary condition, right? And the opposite is for the expansion waves. So if there are expansion waves and there is a free boundary, so an oblique shock, right? So vice versa. Okay. So that's sessions this week's lectures, right? So we will now move on to the questions, right? So moving on to the next slide. So as we have been doing in the previous sessions, so questions have the topics, related topics, right? The topics from which these questions have been taken as the questions have been prepared, right? So question 1, right? Let's see this question. The topic for this question is shock polar. So we have discussed shock polar, which is essentially a hodograph plane. Hodograph plane where we are looking into the velocity components of flow at a particular Mach and uh, deflection, flow deflection really. So the is that shock polar is the graphical representation, right? So yes, uh, then next it says that of oblique shock properties. So this is also right that this shock polar is a graphical representation of shock oblique shock properties, right? And then it says at uh, uh, Mach numbers, right? So so if we look into this question, so the question says that this is shock polar is for shock wave angles. What is shock wave angle? Shock wave angle is nothing but beta, right? At different Mach numbers, right? But from our knowledge, what we have seen is that shock polar, yes, indirectly we can say that there is beta is also included in it, but then uh, from the this uh, that we link this shock polar to the deflection angle of this particular flow direction, right? By virtue of which we get oblique shocks. So in any this in this case, uh, though B is the graph representation, right? So if we see the option, so it's a true or false type of question. So we would give it a false because theta is directly linked to the shock polar, right? And the velocity is linked to that theta. Right. So yes, the answer is also B. Right. But uh, we are happy with this all this knowledge, right? Okay. Then there is this next question, right? Let's see the next question. And, is on shock polar. again on shock collar. So this question says, let's see what it says. Okay. So question says, as the deflection angle is increased, the x velocity component of the flow across and the x velocity component of the flow across an oblique shock in the blank. Right. So this is a fill in the blank type of question. So we have to give our answer as per the given options, right? So it increases. Second option is it decreases, right? Third option is it remains constant. And the fourth option is we cannot comment directly based on the information we have in our hand. Right? So the question has talked about the deflection angle. So what question says is that we are increasing the deflection angle. Right? So the x velocity. So the question directly doesn't ask us to use shock polar to solve this question, but we can solve it using shock polar. So if you see okay, so the x. So if you see this, you can draw a shock polar, but answer it. So if I draw a shock polar, right? So this is our origin rate. So the question has asked about the x point, right? This is the very less theta value, right? Theta 1. Then there is, let us suppose there is one more point. Let's say this is A point, this is point B. So for B point, we have theta 2, right? So this is increasing. And then let's take one more point, right? C. So this is our theta 3 point, right? C. So theta 3 point is there. If you see the x velocity components of all these three cases, so if you see for this A case, right, and then you see for B case, then you see for C case, right? So for C case, we have this much velocity, right? You can call it Vxc, right? For and for A case we have this much velocity, right? So clearly we are when the 3, right? When theta 1 is less than theta 2 is less than theta 3, right? So for this theta 3, right? So for theta 3, we have this C, Vxc, which is the least, right? So for theta 1, which is A case, Vxa, right? It is the X component is the highest. So this means that as we increase the deflection angle, this X velocity level. So if we see options, so B option should be correct, right? So if we see the answer, so the answer is B only, right? So the X velocity component across an oblique shock decreases with the increase in the deflection. Okay, so this question was based on shock polar only. Previous question was also on shock polar. We have a few more questions on shock polar because it's an important topic, right? If from this course perspective also and from this week's content perspective also. So we have that the locus. This question is also based on shock polar. Right? The question says that the locus of all possible velocities ahead the shock. So locus of all possible velocities, right? So when I discussed shock polar, so I told that it is a locus of all the velocities for different theta deflection values of the flow. Head of the shock can be plotted as shock polar at that statement, right? So now the question gives two options whether it's correct or incorrect. So this we have to decide. Right? So this is nothing but basically the definition of the shock polar. Just to check whether we are conscious about what a shock polar is, right? So if we carefully read this of all possible velocities, right? But the statement doesn't say at different deflection angles. We have one problem is this. Then the shock says that ahead the shock, right? So whether those velocities velocities, so that there should not be confusion, any kind of confusion in that knowledge, right? So first is that. Then question says that it is plotted as shock polar at so its question is about that we have some Mach number upstream velocity of this raw shock polar, but then possible velocities whether are ahead of the shock or behind the shock, right? That is we look at this shock polar. When we draw it for the velocities that are behind this shock. It's behind of that oblique shock, right? So this should have been behind, right? But because the question says that it's ahead, so in that case it's a false statement. Right? So it's a false statement. So if we see our this answer, so answer also says that it's B, false, right? So this was our third question, right, of the session. Now we shall move on to the next question. Right? Let's see the next question. Also, right? The next question says that for a weak oblique shock solution, so it has the question discusses the oblique shocks, right? And in oblique shocks also a weak and this weak a weak oblique shock, right? So for a weak oblique shock solution at zero deflection angle, right? So there is no deflection. Now the question also says that there is no deflection, right? And the gamma this question has given is 1.67. Right? Find the approximate m star, right? What is m star? So the question has asked us to find the 0.67 zero deflection angle, and when the upstream Mach number is equal to infinity, right? So the upstream equals to 1.67. In that case, what is our weak oblique solution, right? In that case, what is the m star value for our weak oblique shock solution, right? So for this question, we have one formula that we should know. Only then we will be able to solve this question. Question for solution. So m star equals to gamma plus 1 over gamma minus 1 root, right? What is gamma? Gamma is 1.67, right? Plus 1 divided by becomes 2.67, right? divided by 0.67. So if we work this out, let's just, so this comes out to be 1.9962. 9962, right? This is our answer, right? So this question has given you options, right? So we have four options. A option is 1, B option is 2, C option is 3, and then D option is 4. So we got this value, right? And our B option is close to this value, right? So in that case, this is our correct answer. This is our correct answer. Option B is correct, right? Option B is correct. Four. Right? So now we are into our next question, right? So next question, right? But one hour has passed since the start of this session. So we shall take a 5 minutes break, and after that we shall continue with this session, right? All right. Okay, so let's start. Right? Let's continue with our session. So now we are into question number 5. The topic of this question is the topic on which this question is based is again shock polar. So that's why there are like few questions based on it, right? A couple of questions based on this topic, right? So this question is the question number 5 is inside the sonic circle, all the velocity components have dash values and represent dash shock solution. So, so let's see what the options are. So we have 4 options, right? So 4 different words have been used, right? Subsonic has been used, right? Then supersonic has been used, then weak has been used, and strong has been used. So the question introduces this term, right? Sonic circle. So first we need to know what a sonic circle is, and then the velocity components, right? In that sonic circle. And the values have values. So either it will be subsonic or supersonic values, right? In the sonic circle. And represent dash shock solution, right? So either it's a strong shock solution, right? Where strong shock, the question means it's either a strong oblique shock solution or a weak oblique shock solution, right? So right. So if we see question number 5, let's try shock polar. Right? So we drew this shock polar. Now what is a sonic circle? Sonic circle is nothing but where we have Mach 1, right? So we will draw this one a quarter of a circle, right? In this quadrant, we will draw a quarter of a circle, right? And this quarter of circle is such that the Mach this is our Vy by A star, and this is our Vx by A star, right? And this is our sonic circle, right? So, right. So here, what is the peculiarity of this sonic circle is that here m star is equal to 1, right? So this is our sonic circle. So sonic, if we feed from the graph, it appears that this sonic circle cuts this shock polar at theta max, right? So we have seen in this theta beta m curve, right? If you see the theta beta m curve, just also. So here this is theta max. Below this there are weak shock solutions for some theta value, right? Now we see our shock polar. So let's say again if there is some point A, right? So if we draw from origin a line, right? So it cuts this line cuts this cuts is A and the other one is A dash, right? So this line cuts the shock polar at A dash and A. And in these 2 points, A corresponds to the weak solution, right? And A dash corresponds to the strong solution. Right? And if you see your sonic circle, so this strong solution falls in this sonic circle. The oblique shock solutions, obviously, we know that in strong oblique shock solutions, across that oblique shock, the MAC value is less than 1. Right? For weak oblique shock solutions, it is always greater than 1, right? Behind the shock. But for strong oblique shock solutions behind the shock, the MAC value is less than 1, right? Which is nothing but subsonic, right? So this was a sonic circle, and then there was uh, they are weak and strong oblique shock solutions. So now if we come to our question, so inside the sonic circle, all velocity components have these have subsonic values. Obviously, it will be subsonic because the whole radius is of unity. So the components obviously will be less than 1, right? And represent dash. So whether it's a strong or weak. So I just mentioned that. So this is strong oblique shock solution, right? So A was a weak oblique shock solution. A star was a strong oblique shock solution. So to the left of this theta max, right? If we max value, we say that this is our theta max value, right? We say that this is our theta max value. In that case, left to the point B in shock polar, we have strong oblique shock solutions, and to the right of B, we have weak oblique shock solutions. So from the options, if you see, option question. And if you see the answer, so the answer also says that B option is correct, right? So this is our answer. Now the topic was shock polar, right? So we have already done 5 questions on shock polars. Now let's see the next question. Question number 6. This again on shock polar, right? So here we have this videos only. This diagram is from this either lecture 18 or 19, right? So the question says that for a specific Mach value, the farthest point lying on the abscissa. So what is an abscissa? Right? So a Mach value has been given. So farthest point. Right? Now what is a shock polar? We know, right? So it represents A dash. Right? Is coordinate. And ordinate is the y-axis, right? I hope you know this. Abscissa is x coordinate and ordinate, not coordinate but so let's see the options first and then after that we will decide how to answer this question. Okay, so if you see point A, few inferences, one at least one inference you can make from uh, this point is that angle theta is equals to 0 degree. So we know if theta is 0 degree, right? So either we get a normal shock, right? If it's a strong solution, right? And if it's a weak solution, in that case, what we get is a Mach line, right? So in this question, first we must know what is abscissa, right? And then we must know that the farthest point, right? The points right to the theta max value on shock polar belong to weak oblique shock solutions, and to the left of theta max value they belong to strong oblique shock solutions, right? And the weakest solution belong. So the options we have is A is Mach line, B is normal shock, C is oblique shock, and then D is none of the above. So clearly we have an answer, right? Option A is correct. Right? Shock polar. Now let's first of all see the answer. The answer is A, and then we'll move on to our next question. Right? So next question is on regular reflections of oblique shocks, a topic from lecture 18, right? So here we will we have so from a primary wall we get an oblique shock, and then it strikes a secondary wall, and from there whether it reflects or something else happens, that has been discussed, right? So based on that, let's look into this question number 7. So if you see the options, it's a true or false type of. So whether a reflected shock is weaker than the incident shock. So we need to answer that, right? So if I draw this, or let's look into the already drawn, right. This is here, this diagram is where this is primary wall we have, then there we have secondary wall, right? And this is flow direction, and the oblique shock has been mentioned, right? And then oblique shock, this strikes at point A, right? So if I say this as region 1, this as region 2, and this as region 3, so if M1 is the MAC at region 1, right? And M3 is MAC value at region 3. We know across a shock, the MAC value decreases, be it normal shock or oblique shock, right? So What it means is that and the strength of the shock also depends on the upstream value of the Mach for the flow, right? Upstream of the shock, right? So as M2 is less than M1 theta, right? So for same deflection angle theta, so we have this theta, then this at the secondary wall also the deflection will be theta. So M2 is less than M1. In that case, this second oblique shock, right? So if we call oblique shock as AB, so AC oblique shock strength will be less than that of AB oblique shock. Why so? Because the Mach for AB, the upstream Mach for AB oblique shock is higher than the upstream Mach for AC oblique shock, right? So this is the expression. Question says that a reflected oblique shock Mach is less for the reflected shock, so it is weaker than the incident shock. Right? So this is a true answer, right? It's a true statement. And if you see the answer also says the option A is correct, right? So this was on regular reflections of oblique shocks, right? So moving on to our next question number 8. So this question was on regular reflections of oblique shocks, right? Last topic of lecture 18. Now we have question number 8 in front of us, and the question is on intersection of oblique shocks. Okay. So here we have intersection of same family and of different family of oblique shocks. Right? So let's see. The first question is on opposite family of oblique shocks, right? Question number 8. It says that the two oblique shocks of opposite family dash after. So we have four options, right? So these oblique shocks either reflect or diffract or none of the above. So do we have some correct answer to this question, right? So from the this uh, lecture 19's content only, right? Only if you see this opposite family of opposite family. Hmm. Let's say this is A, let's say this is B, let's say this is C, right? So the slides also, the content also says that when there is intersection of these oblique shocks of opposite family, in that case there is refraction of these shocks, right? Refraction means there is some change in the direction of these oblique shocks, right? All right. If you see the options, right? The option B says that these two oblique shocks of opposite family refract, right? So next question. The answer also says this. Okay. So moving on to our next question. Right? Of oblique shocks, right? So the question says that in case of intersection of two oblique shocks of opposite family, right? So intersection is taking place of two oblique shocks of opposite family, like it was in the previous question, across the slip line, right? So now we need to know what a slip line is. The velocities are not in the same direction, right? So what is a slip line and why do we define a slip line? So intentionally I had not drawn a slip line on this particular diagram, right? Because I wanted to discuss it now only. So I'll just draw the directions, right? Right. So if you see this theta A and theta B can be different, right? But in that case also, when this flow moves, right? So let's say it's so regions. Let's these regions. Because say if the theta A and theta B have different values, even then across this oblique shock, when the flow moves in both these oblique shocks, so one direction only, right? It cannot move in two directions, right? So because it has to move in one direction, right? But then because these are two different oblique shocks, so there are some differences in these two flows, right? So what difference is there in these two flows from two different oblique shocks is that though this direction of the velocity will be same, right? And the static pressures for these two cases will be same, because if there are difference in the static pressures, obviously this cannot move in one direction, right? Because in some these will move in one particular direction, but even then, because the theta values, the deflection angles are different for these two different cases, so the entropy change this across these oblique shocks is different, right? And to differentiate this particular difference, right? The flow, to differentiate the two flows because of this uh, specific difference, we draw an imaginary line, right? And we call this line as slip line, right? So this is the slip line where the, so we will say after 3 we have flow in fourth regime, right? As right? So these are the two regions, right, where the pressure, static pressures will be same, the flow directions will be same, but the entropy change has been different, right? For the same initial upstream MAC value that was in region 1, right? So the question says that, though the question is very basic, so but we discussed the whole concept of slip line, right? The whole idea of slip line. So across the slip line, the velocities are not in the same direction. That is not true, right? They are in the same direction. So the answer to this question is false, right? Option B is correct, right? Okay. So now let's see the next question. So this question again is on intersection of oblique shocks, right? And the question, this is question number 10, right? So this question says that in case of intersection of two oblique shocks of opposite family, again we are discussing opposite from family. We just discussed opposite family and now we are again discussing opposite family. In case of intersection of two oblique shocks of opposite family, across the slip line, the static pressure are different. Static, it should have static pressures. The static pressures are different. So is it the case? Clarified it that there cannot be static pressure difference across the slip line. We draw the slip line only because there are entropy differences in the two regions, right? When we talk about the this intersection of oblique shock, so the static pressures are same, right? So the answer to this question is false. B is the correct option. So if you see the answer says that it's B, right? All right. So this was our 10th question on intersection of oblique shocks. Right? So till now we have seen 6 questions on shock polar, right? And then one question was on the last topic of this lecture 18, that is regular reflections of oblique shocks, right? And then we saw this intersection of oblique shocks after that. So we have discussed 3 questions on this oblique shocks of oblique. Right? So moving on to next question. Let's move on to next question. So this question again is on the same topic, intersection of oblique shocks, right? Question number 11. Question number 11 says that in case of intersection of two oblique shocks of opposite family, there will always be a slip line. So this is an interesting question, right? So whether there will be always slip line in case of opposite family of oblique shocks. Okay? So this is a true or false type of question. Okay? So to correctly answer this question, we need to be clear on the point that what is an opposite family of oblique shocks. Right? So I have discussed it that we call such oblique shocks, sorry, we call such oblique shocks as of opposite family when there are deflections in opposite direction, right? As is the case with this particular diagram. Right? So AC is left running wave, and then BC, for BC case, this is a right running wave. And when such waves interact, right, such waves are known as oblique shocks of opposite family. This definition nowhere says that the deflection angles have to be same or different, right? This definition does not specify that. But these, what will happen is that conditions at 2 and 3 regions will be same, right? Because deflection angles are same, upstream Mach number is same, which essentially means that they both are of same strength, right? The only difference is the direction, right? Direction of deflection. Other than that, these are same, right? So which means that across the refracted shocks, right? Across the refracted part of these shocks also, right? That is region 4 and 4 dash. In that also everything will be same. In case there is no need to define a slip line because the entropy changes will be same for both the regions, that is 4 and 4 dash. Right? So in case when the deflection angles are same for the opposite family of oblique shocks, in that case we do not need to define. It says that in case of intersection of two oblique shocks of opposite family, there will always, right? It says that there will always be a slip line, but that is not the case, right? In case the deflection angles are same, in that case, this statement won't be true, right? So in general, we can say that this statement is false, not true, right? So this is our question number 11. B, right? Then there is question number 12, which says that wave reflection from a free boundary. Sorry, this is the topic, right? So the topic is wave reflection from a free boundary. Right? So now these whether it's an expansion wave reflect from a free and not a solid boundary, right? Not a solid wall. So in that case, what happens, right? So if you see that, so question number 12 says that from a free boundary, an oblique shock reflects as an oblique shock. So our knowledge says that an oblique shock, right, reflecting from a free boundary, as is the case of nozzle with the over expanded case. In that case, we get an expansion wave and vice versa, right? So if the statement says that from a free boundary an oblique shock reflects as an oblique shock, that this statement is not true. Right? So this statement is correct. Now let's see the next question, right? So the next question, so we have this these uh, okay. So I was saying that we have this data for 4 questions from 13 to 16, right? So for that, right? So the no, yes. So it's of this. First of all, there is this. It's kind of regular reflections of oblique shocks, where we have first we have one oblique shock, and then when this oblique shock strikes at some place on the this secondary wall, right? So this is primary wall. This is secondary wall. So when it strikes on the secondary wall, at that place also we have given some deflection of theta 2, right? First of all, at primary wall we have theta 1 deflection, and at secondary wall we have given a theta 2 deflection. And the related angles are there, right? So shock wave angle also have been given, right? Theta 1 for the this primary for the shock attached to primary wall, and then beta 2 for this shock attached to secondary wall, right? So in that case, some information has been given to us, right? So upstream MAC is given as 2.5, right? And upstream this pressure also has been given, static pressure has been given as 1 atmosphere, right? And what also has been given is T1 has been given as 290 Kelvin, right? And theta 1 has been given as 12 degrees, and theta 2 has been given as 6 degrees. Other than that, we have given. So let's see how to use these things and solve our questions, right? So we have first question, 13 question to find the Mach number at region 2, right? So if we see question number 13 solution, right? So we have M1 equals to 2.5 and then P1 equals to 1 atmosphere. So theta 1 is given as 20 degrees. So, right. All right. So if you see a formula, right, from our previous knowledge, so let's see if the formula says, yes. So it says that M1 equals to Mn1 by sine theta, right? Right. So beta, okay. So from M1 and this theta 1 value, we can get beta 1 value, right? Which is 35.8 degrees, right? And then we can find out Mn1 from this M1 equals to Mn1 by sine beta, right? And which will come out to be 1.46, right? If we work this out. And then if we find out, because we have done such question in previous session also, but shall repeat this also, because we know that mn square equals to n divided by 2 gamma by gamma minus formula, right, for mn2 square. So from this formula, mn2 square comes out to be 0.5122, right, which implies if we take the square root of it, right, mn2 comes out to be 0.7157, right? And now we know that m2 equals to mn2 divided by sine beta minus theta 1, right? Beta 1 minus theta 1. So if we work this out, it comes out to be 1.7736, right? So this is our answer to question number 13, right? Now, if you see the answer, it is 1.77. Now the question, next question says that calculate the MAC at region 3. So to calculate at 3, what we will do, we have M2, right? And then because we have theta as 12 degrees plus 6 degrees, right? Right. 18 degrees, right? And for that, we have this beta 2 value as 60 degrees, right? So in that case, are this normal component, normal of this flow that is in the second region, and that is also is upstream to the this second shock, right? This shock that is coming from the secondary wall, right? Okay. So the shock that is region 2 as the upstream flow, right? So let's denote this the normal component of that as dash, right? Mn2 dash. And how we can find it? We can find it using this particular, right? Because 1 here means it's upstream, right? And for our second case, for our second oblique shock, 2 is the serving as 1, right? that is why I'm writing it in this fashion, right? So in that case, mn2 dash comes out to be 1.77 into sine 60 degrees, right? Which comes out to be 1.5328, right? And then we use again this mag across the downstream of the shock if we need to find. So we will use this again, this formula, right? So 2 will replace 3, 3 dash equals to 0.4771, right? And mn3 we will get as 0.6907, right? And then again we will use this formula, right? m2 equals to mn2 sine beta 1 minus, but here what we will do is 2 will change 3, right? And beta 1 and theta 1 will replace beta 2 and theta 2, right? So here m3 will come out as 1.0322, right? If we work this out, it will come out as 0.0322. So it's calculated value, so you can let me know, right? All right, so this was about question number 14. And if you see, so while using this formula, right, m2 equals to mn2 by sine beta 1 minus beta sine beta 1 minus theta 1. So in that case, whether I have taken the correct theta value or not, I doubt it, but I believe I have taken correct value, right? But if there is some mistake, please let me know, right? All right. So this was about question number 14, right? Now, if you see, calculate the static pressure at region 3. So how we can calculate from table only, we can see all that, right? So P2 by P1, if you see the table, P2 by P1 is given as 2.1 for our first case, right? Where we have this Mn1 as 1.46. So for this case, we have P2 by P1 as 2.1, right? So P2 will come out to be 2.1 atmosphere, right? Now this P2 will serve as upstream for the second oblique shock, right? So P3 by P2 is given as, right? Normal component as 1.53, right? 53, right? So for that, the corresponding pressure value is 2.6, right? So which implies P3 is 2.1 into 2.6, right? Which comes. So this is about our question number 15. Now the last question is calculate the static temperature at region 3 in Kelvin, right? So if we see the same way we will do in this question number 16, that is our last question, right? T2 by which is 348 Kelvin, right? And then for second oblique shock, the upstream region is 2 and the downstream region is 3. So for that, T3 by T2. Let me check once again. Okay. So it is just 1.4, right? Okay. So 1.4 when multiplied by 348, so when multiplied by 348, it gives 487.2 Kelvin, right? So I have figured it out, right? So that's why I have some other answer in my slides, but that's okay. So we have this 487.2, right? 1.4 into 348. Yes. So this was our last question, right, of this session. 487. Answer is 487.2, right? So okay. So this was last question of this session, right? Okay. This is one reference. Then there was one doubt the previous session, right? Question 12. So for this, one can refer to lecture 17, slide number 14. So from there, it will be clear that the answer to this question is B. Sorry. If I is smaller, which so there you they are giving theta and here they are giving mach, right? Theta max, I believe, something like this. This is for cone and all right. So this is it, right? Uh, week 8 live tutorial session, right? We moved in the same fashion as we were moving in the previous session. So we discussed uh, the topics, right? The lecture topics that were discussed. right? And one new thing we included in this session is we previous year discussed, right? Doubts were discussed. In the next session, session number 9, with the same day, right? That is Sunday, and with the same timing, 3 p.m. to 5 p.m. Right? Till then, I'll say goodbye.